But we have another options too. As good engineers, we like to have two options and then take the one that is more convenient in every case. We'll see that there are cases in which one could be easier than the others. And that is the following. Again, in the second analogy, we start from the problem, for the thermoelastic problems, but now we have here the stresses, we have the equilibrium equation. Here we have the constitutive equation. In that case, for convenience, we talk about the inverse constitutive equation. So the strains are the elastic strains, C minus 1 times sigma, plus some thermal strains, which, as I recall, were computed as alpha delta theta times 1. Alpha being the, what is the name that it did to alpha? Remember? Thermal expansion coefficient, okay, a property of the material. And then the geometric equation, which is the, as ever, and this is the displacements, the boundary conditions in terms of displacements, and the boundary conditions in terms of the stresses at gamma sigma. So this is the original problem. And now we are going to do the same procedure, but in different way. So we are going to rephrase this problem such as to obtain a problem that doesn't involve apparently temperatures. And that's the way we do that. Look, originally we have that actions, body forces, tractions, prescribed displacements, and temperatures. And these are the set of equations of this problem, boundary, partial differential equations plus boundary conditions, and then we obtain the response 1, this is action 1, after introducing that into the machinery, by the way, that we don't know, because this machinery we don't have because it involves temperatures, we would obtain the displacements, the stresses, the strains and the stresses, okay? So now we do the following. First, look, you know that given a strain field, we can obtain the corresponding displacement field. You know that. We did that in the second chapter of this course. You remember? That is what we call integration of the strain field, okay? So now let's consider the thermal part of the strains, these thermal strains here. And let's see what would be some displacements which are compatible with these strains, okay? We know how to do that. It's a preliminary problem. Integrate these strains to obtain some displacements. These displacements are called thermal displacements, UT, okay? So, okay, we know the strains, which are given being the symmetric gradient of some displacements termed the thermal displacements, and we have to solve this system of equations. And we know how to solve it. You know that there were two stages, you remember? First stage to know the rotations, second stage to know the displacements. But we also know that it's not always possible to solve the problem. In order to having some displacements, some strains, obtain the corresponding compatible displacements, we need something to be fulfilled by these strains, compatibility equations. So these strains cannot be, if I give you a general defined, invented, made up strain field, it's not always integrable in the sense that there's not always a displacement field that fulfills these equations. In order to do that, that displacement field has to fulfill the compatibility equations. Let me just keep the remark at this point here, saying that, okay, let's assume then that this distribution alpha delta theta 1 is a strain field which is compatible. If it's compatible, then we can obtain some displacement field that fulfill that the symmetric gradient of this strain field is equal to the thermal strains. If we know that, then once we have integrated that and computed the thermal displacements, we can define the non-thermal displacements as the difference of the original ones that we don't know, minus the thermal displacements that we know, because this one, this is known, and as a preliminary stage, we can compute these thermal displacements, okay? So we can state this equality. The total displacements that we don't know are equal to the non-thermal displacements that we don't know yet, and the thermal displacements that we know from after integration of these equations here. So now the point is to compute the non-thermal displacements, which summed up to these thermal displacements will provide the original unknown. Okay? So the first step. So now, if I look to the geometric equations, to these equations here, the geometric equations, okay? So now, which is said that the strains are the symmetric gradient of the displacements, if I replace that solution in the displacements, the strains are the symmetric gradient of the non-thermal displacements plus the thermal displacements. Since this is a linear operator, the symmetric gradient of the sum is the sum of the symmetric gradients, so we can write that. Okay, that is by construction the thermal strains, because that is the way I compute these displacements, obliging that the symmetric gradient of these thermal displacements equals the thermal strains. So it's that here, and then that is what the symmetric gradient of non-thermal displacements that I define as the non-thermal strains. So finally, I have another split of the strains into the non-thermal strains, which are the symmetric gradient of the non-thermal displacements, plus the thermal strains, which are the value that I know, alpha delta theta times 1. Okay? And what about the boundary conditions? The boundary conditions that initially were set at the gamma u, the u equal u star. That means that u, which in turn is equal to the non-thermal part of displacements plus the thermal part of displacements, then can be written like that, and then I can pass that term here to the other side. So the boundary conditions are rephrased or modified, saying that the non-thermal part of the displacements are equal to the original prescribed displacements minus these thermal displacements at the boundary gamma u that I have computed in this preliminary state like that. Okay? So this is the procedure. I first integrate the thermal strains. I obtain, this can be trivial sometimes. That is the key point. If that is trivial, that is not involving an extra cost. If that is very complicated or even non-possible, then we are in trouble. Okay? But now I compute this. Now, after that, I modify just the boundary conditions, imposing that where I had to impose u star, I impose u star minus u thermal. And that's it. So the problem now can be rephrased like that. That is the equilibrium equation, which is unmodified. The constitutive equation now is given on the thermal part of the strains. So the non-thermal strains equal, that's the inverse Hooke's law for isotropic material. And then the strains are already formulated in the non-thermal part of the strains as a symmetric of the symmetric gradient of the non-thermal part of the displacement. So this is a problem where no temperature appears. It's a problem where I have stresses, non-thermal strains, and non-thermal displacements. And the boundary conditions, that's important, that is corrected by subtracting to the prescriptions that I have in gamma u, the value of the thermal stress displacement in this gamma u. So I have constructed a problem that we call the analogous problem. The analogous problem is a problem where the actions are the body forces, which are modified, okay? The temperature, the tractions at the boundary, gamma sigma, which are unmodified. And now the prescriptions at the boundary, gamma u, are modified to this u star, the original ones, minus u thermal. That's the part. So I modify the prescriptions only at this part here, okay? And what is the result? Well, the results, according to that, this is a problem with no temperature involved. So I know the machinery for that. I just use, for instance, the Navier equations to solve it. And I obtain, the solution of this problem will be the non-thermal part of the strains, the non-thermal part of the total displacements, the non-thermal part of the strains, and the real stresses. So the solution, the response would be that. So actions that too introduced in this machinery that is a pure elastic problem provides the response. That's problem 2. So this is different from that. What is the difference? So if we do that, we just establish what is the difference in actions of problem 1, the original one, and problem 2, which is the analogous problem, non-thermal problem. Well, in terms of the body forces, I haven't made any change. In terms of the prescriptions, yes, I've done. Here they were U star, here the prescriptions were U star minus U thermal, so the difference is U thermal. In terms of the tractions, prescribed tractions, I haven't done any change. And in terms of temperature, here there was temperature, here is not. So the difference is delta T. That is what we call the difference of actions 1 minus action 2 is what we call action 3. And what about the responses? Well, the original responses were supposed to be the total displacements, the total strains, the total stresses. The problem 2 is a problem formulated in terms of the non-thermal part of the displacements, the non-thermal part of the strains, and the full stresses. So the difference would be a vector which has as actions, or as response, sorry, the thermal displacements, the thermal strains, which is this that I know, and 0. So look, I know this, I know that, because after integration I know that. This response is known. This is what, and then it can be proven just by replacement that if I replace these actions and these responses into the problem, into the original problem, these are solutions of the thermal problem under these actions. So finally, I can talk about one action system 1, which is equal to action 2 plus action 3, and the response 1, which is equal to reaction 2 passed to this side plus reaction 3. Okay? So let's synthesize the problem. The situation is the following. I had the original problem, which was thermoelastic. Then I have in that problem characterizing some actions, which are the body forces, the tractions, and the prescriptions, and the temperature. And I'm looking for the solutions in terms of the total displacements, total strains, and total stresses. Now, I just decompose the problem into 2 parts. One part which is trivial. I don't have to compute that. I'm just paying attention to the solution of that, which is, in terms of displacements, the thermal displacements. In terms of the strains, the thermal strains, and in terms of the stresses, 0. It's like a free expansion. There are no stresses. Okay? No stresses. And the problem I have to compute that is one in where I don't have any temperature. The body forces are the same than the original ones. The tractions are the same as the original ones. I have to correct the prescriptions at the boundary part of the problem where I had the displacements prescriptions. I have to correct them, and after that I obtain a solution. How do I obtain the final solution? By summing up these two. So after that solution that I have obtained here, the sum to that solution, the thermal displacements that I've computed in the first initially, and I will obtain the real final displacements. In terms of the strains, I sum to these strains the thermal strains, and I will obtain the original strains. And in terms of the stresses, I don't have to correct them because this is 0. Okay? So this is the second analogy. You know, look at what we have. In both cases, in the first and the thermal analogy, we have always the decomposition of the problem into the original thermoelastic problem into one analogous problem which is elastic, no temperature is involved, plus a correction. We solve that problem as we are used to, using the machinery that we have in the formula it's available, and then we have to add to that solution that. What you have to correct and what you have to add depends on the analogy. In the first analogy, you have to correct the body forces and the tractions in terms of something that you know and that depends on temperature. Of course, if there is no temperature, the corrections are zero. Okay? And then, once we obtain the response, we have to correct this response just in terms, in the first analogy, by subtracting or by adding the thermal stresses. Okay? Subtracting these thermal stresses. And in the second thermal analogy, then the composition is similar, but the way that we do this the composition is specific. So the original problem involves some unknown quantities and some data. We just, as a preliminary stage, compute the thermal displacements by integrating of that thermal strains, which are known. We integrate these equations, we obtain thermal stresses, and then we are ready for solving the problem in the analogous problem 2, which is no thermal, no temperature involved. Just by correcting, keeping all the actions the same, but correcting in the prescriptions in terms of displacements, subtracting these thermal displacements. We solve the problem, and once we have solved that, we have to add to these non-thermal displacements the thermal displacement that we have computed in the preliminary stage. The strains, just have to correct that by adding, summing up the strains, the thermal strains, and we don't need any correction on the stresses. That's it. Look, maybe at this time I can go to some of your previous knowledge in structural analysis. Have you ever done in your courses of structural analysis, have you ever accounted for temperature? You remember, what did you do? I remember from my courses on structural analysis that I was taught to do the same. Let's consider the structure that was initially subjected to some increment of temperatures. Okay? Let's release the boundary conditions of the original structure so as to make the structure isostatic. Okay? And then let's the structure deform under the temperature. And then let's reconstruct the original boundary conditions by imposing displacements at the boundary so as to retrieve the original boundary conditions. That is that. So we did a sort of decomposition. So look, that's the simplest case, but it's sufficient for our purposes. Imagine that you have this clamped, double clamped at both ends beam subjected to a constant increment of temperature, right? Our knowledge on structural analysis said, well, to solve that, first we release, for instance, this side as to make the structure statically defined, what we call isostatic. So now that is a cantilever. Let the structure deform in terms of this delta temperature. If the temperature is delta T, then alpha is the expansion coefficient. So how is the beam, the cantilever expanding? Well, it would have a temper. We know that the temperature would be alpha delta theta. So the expansion would produce a displacement field that is alpha delta theta times x, and specifically at the end, at this end, the temperature will be half delta theta times L. Okay? And then what did you do? Just consider, after considering that, no stresses here, because it's statically defined. Then just we retrieve the initial boundary condition. So we just produce an imposed displacement at this site, which is minus alpha delta t times L, to retrieve the original boundary condition, because this couldn't move. That's the way that you were taught, much more probably, to do for thermal problems. Look, that is nothing else than the second analogy. So this would be the original problem. That problem in which we correct the boundary conditions, the original boundary condition that said that the displacement here had to be zero. Just we correct them, imposing here the original displacements, zero, minus the thermal displacements, minus alpha delta theta times L. This is state 2. which is elastic, no temperature is involved. And when we solve that, what can we say? Well, the strains, the displacements would be the one that we have here plus this. For instance, that point would be minus ut minus alpha delta theta times L plus alpha delta theta theta. So it would have 0. The strains here are 0. No, 0 no. Well, in that case, could be 0. Okay? Thermal strains here. So now the strains would be the one that we have here plus the strains alpha delta theta times 1. And the stresses are 0 here, so the stresses are those here. So that's the second analogy. Now you know what is the interpretation of this second analogy. The second analogy, or the way that you solved typically the thermal problems in a structural analysis, is just by specific applications of the second analogy. Second, you know that you have another way to do that, which is to apply the first analogy, which is less intuitive, if you want, less structural, but maybe more convenient for solving problems than this one that you went at. So, let's compare the advantages, possible advantages and disadvantages of the first and second analogy. So, first, the second analogy is the one that you know, is more intuitive, is what we said, no? Let's decompose, release one support, make the structure statically defined, and then apply the thermal expansion, and then recover the boundary conditions so as to retrieve the original ones. Remember, that's structural, okay? But, very important, you are just considering here that you know this displacement. These thermal displacements, when we say, let's the structure expand, well, that expansion cannot have doesn't have any solution. Because when we say, let's the structure expand, that means let's compute the thermal displacements. And this thermal displacement field may not exist. Okay, because that is not always integrable. Of course, if the temperature is constant, then it's trivial.